Alright, and hello to momentum in 2 dimensions. So, one thing about this is not on the test. This is just for your case files. Now, that isn't to say that there might not be some sort of extra credit, something or another on the test, but you do not have to know how to do this on your own. I expect you as a group to be able to do these problems, but on your own, not so much. Alright, so let's go ahead and get started. What we know is that momentum before a collision has to be equal to the momentum after a collision. We call that the conservation of momentum. But so far we've only been dealing with one direction, stuff going either in the positive x or the negative x. So let's go ahead and say, well, this is the x momentum initially and the x momentum finally. Turns out that the initial x momentum has to equal the final x momentum. It turns out that this is also true for stuff in the positive y and the negative y direction. The initial y momentum must equal the final y momentum. Alright, now when you're dealing with 2 dimensions, that means that you have some x momentum and some y momentum, and you got it going on at the same exact time, and that's what gives you some diagonal momentum. Here's the thing, though. Diagonal momentum is not conserved. The math just doesn't work. So we have to break it down into its x and y components. We have to break this net momentum and break it into a y momentum and an x momentum. Alright, so, a little bit of math stuff. You have gotten this before, but it's been a while. So, here you have your net momentum. Here you have your x component of that momentum. And here you have your y component of that momentum. Stuff you know. This is some angle represented by Greek letter theta. This is your net momentum. This is your y momentum. This is your x momentum. Where, remember, your net momentum, that's going to be equal to the total mass times the speed, the velocity at this point. Alright, now what are these things equal to? I don't know. Triangle stuff. First thing you need to know is Pythagorean theorem. A squared plus b squared is going to equal c squared. Alright, now other things. We know that sine theta is going to be equal to the opposite over the hypotenuse. So if I know theta, and if I know my net momentum, I can find my y momentum. Cosine theta is adjacent over hypotenuse, so I can solve for the x component of my momentum. And just in case I want to do it this way, the relationship between the y momentum, the x momentum, and theta. Here's the thing that you need to do in your case files. You will know mass A, you will know mass B, you're going to know the delta x for after the crash, and you're going to know V final for after the crash. You are then going to solve for m total. Hopefully you can figure that one out. Oh, you also know the acceleration from friction. Sorry. And you're going to solve for the initial velocity after the crash. So this would be the velocity of the two cars stuck together right after the crash. Because remember, in case file 7, you got a car going this way and a car going this way, and they collide, and then you get a big ol' wreck going that way. Alright. You find this. Then, find P net. Where P net equals M times V. Alright. Then, you need to break it into your X and Y components. So you go from P net to PX after the crash, and PY after the crash. And here's why you care. PX after the crash has to be equal to PX before the crash. And PY after the crash has to be equal to PY before the crash. Here's the picture before the crash. Ask yourself, does this car have X momentum? Does this car have X momentum? So the total X momentum is going to be the X momentum here plus the X momentum here. Next question. Does this car have Y momentum? Does this car have Y momentum? The total Y momentum must be equal to this Y momentum plus this Y momentum. Once you have solved for P net, and then broken it into X and Y components, the momentum after the crash X direction, the momentum after the crash Y direction, that will then let you figure out the before momentums. And then from there, you can solve for other stuff. And that's where I am leaving it. The rest of it, you got to figure out. All right. Now, all of these notes that you just took, that better have been on page 61. I want you to now work on case file number 7 in your groups, your assigned groups, on page 60. If you would like to go over an example problem with me, keep watching, and we will do it on the bottom of page 61. If you and your group are good, you can stop now and just start working on case file 7, and then move on to work time, free work for your project. If you are still watching, we are on the bottom half of page 61. We are doing an example problem. Here's the example problem. We have a 1,500 kilogram car going east, and a different 1,500 kilogram car going north. They collide, stick together, and go off at 11 meters per second at 30 degrees north of east. What were the initial velocities of the cars. Alright, so we got before the crash, we got the crash, and we got after the crash. I'm going to draw pictures. I'll call that A and call that car B. Alright, now, the crash itself happens. Alright? I'm not sure how to draw a picture of that. There. Afterwards, they got this horrible mess of car that's going off at 11 meters per second at an angle of 30 degrees north of east. Because this direction is east, this direction is north. Somewhere in between the two is norther than east. So it's north of east. Alright, you have the problem. You have a sort of idea of what's going on. Let's figure out what's important. Let's see, we got two masses. We got one going east, one going north, as shown in the picture. They collide and stick together, that's important. Then afterwards they're going 11 meters per second at 30 degrees north and east. What were the initial velocities of the cars? Oh. Huh. Well, according to the notes we just took, the first thing I should find is my net momentum. Once I find my net momentum, I'm going to find my x momentum and my y momentum. Once I have found my x momentum and my y momentum, I am then going to find, this is both for after the crash, I should point out. Then I'm going to find the x momentum before and the y momentum before, leading me with a velocity for car A and a velocity for car B, both of which before the crash. Alright, let's go ahead and get started. Let's see, this is going to be mass times velocity. Well, the total mass, that's going to be 1,500 plus 1,500 times 11. Alright, well, that's 3,000. 3,000 times 11 equals 33000. Alright, now I'm going to do my nifty trig stuff, where this is going to be and so my x momentum after the crash, the x component of this momentum, is going to be that times cosine of theta equals 28578.8, where my y momentum, the y component of my momentum after the crash, is going to be 16500. Alright, what about before? Well, it better be the same. If it's not, you just broke physics. Conservation of momentum states that the momentum before has to be equal to the momentum after. Now here's where things get weird. Let's look at car A. Does it have x momentum? Yes. Does it have y momentum? No. Car B. Does it have x momentum? Yes. Wait. No. No, it does not. Look at the direction it's going. It's going this way. That's not in the x direction, that's in the y direction. So it has y momentum, but no x momentum. So that's going to be that, m times v, m times v. And I can now solve for those velocities. Giving me a positive 19.05 meters per second. And .11 meters per second. Positive. And yes, those positives are important because they tell us the direction. You have to give me a direction. You only have two ways of giving me a direction, either with a sign or with an angle. Alright, there you go. More hints than I've ever given any class previous on how to do case file 7. You can figure this out now. I gave you the hard part. Go.